So we will begin with Unit 3 today, and the first theorem that we will be talking about in this unit is the fundamental theorem of line integrals. So what it states, according to this theorem, if you have an analytic function f, let f be an analytic function, writing its components also, uh, be analytic in a domain D, in a domain D, and C zt is xt plus iyt be a contour in D, and suppose this contour connecting point z naught to z1. Suppose this is a contour. So what this theorem says that this theorem says then that the line integral of the derivative of this analytic function, the line integral of derivative of this analytic function over this contour C is nothing but it can be computed as a line in a value of f at z1 minus value of f at z1. So what you have a domain, and in that domain you have an analytic function, and suppose you have certain contour here which connects z0 with z1, and this theorem says that whenever you have to compute the line integral of the derivative of this function, then that line integral depends on C, because this line integral is computed solely in terms of the terminal and initial point of this contour. So that means it doesn't depend upon the path. That means if I take another contour this way, and if I take whatsoever contour I take, but the only thing is that if it starts from z0 and it ends at z1 over each contour, let this is C, let it be C1, and let it be C2. For all the contours, the value of the integral is going to be same. So such an integral is also called path independent. It doesn't depend upon the path. It only depends upon the initial and the terminal. So this also says that the line integral of a derivative of an integral function of an analytic function is always path independent. Let us go to the proof of this theorem, how it's going to be proved. We are going to take two cases since contour is a piecewise smooth arc. So we first assume that it is smooth. First, suppose that this arc C is smooth. So suppose that this arc is a smooth, and what we need to say it is smooth means that its derivative exists. Then by chain rule, what will be the derivative of this function dz f at, sorry, I am taking again the derivative, it need not be derivative here, f of z of t. By chain rule it has to be derivative of f at z of t and z prime of t. So this is it. That means by definition of line integral, I can write this line integral f prime z of t dz. What will be dz of t is z prime of t dt is equal to integral. No, why I am writing? I'm just again writing wrong. It has to be just f of z dz, and this has to be integral a to b f prime z of t, and dz I can write it to z prime of t dt. So let me note this something, an equation this way, or you can also write it in the form of a to b. It is d upon dt. What I just computed above is nothing but this is also d upon dt. It has to be f of z of t into dt. This will be it's this thing. Now let's look at this thing. Why to lengthen it? Let's be clear. You have a function f is defined on domain D. You have a function defined here, and your arc, and within this domain you have this contour here. So by the way, within when we are considering the integral, our integral we are considering the function this f of z of t. It's a composite function. We are considering composition of two functions here, by the way, right now. And so the domain has to be now the parameter interval. Domain has to be now parameter interval. So that means this is now you are considering this composite function as a real valued not real valued function, but domain is real numbers, this interval. And if we consider the component form of this u plus iv, then this implies that f of z of t has to be u of what it you can write it as z is it is x of t y of t plus I times v of x of t y of t. And now apply the integral over it. What we get, this I can write as integral over c derivative of f at z dz, which is equal to a to b d upon dt. It is f of z of t dt. So I can write it in this way: d upon dt. It is using the components of f. It will be u of x of t y of t plus I times v of x of t y of t dt. Now see, now look at these functions here. Look at this function. This is a real function, and again this is a real function. It is a function of t now. So this is a function. I can replace it with another new function u of t. This is just a function of real variable, and it is a real valued function. And similarly with v is also a function of t now, and let me replace it with some other. It is a real valued function. So you can write it in the form a to b. It is d upon dt u of t plus we can be using the linear property of this in the integrals, a to b d over dt v of t dt. Now a real integral. And in real integrals, you can use no because u is a this capital U is a real valued function, and it is being differentiated with respect to real variable. And you can use here the fundamental theorem of calculus from real analysis, the real version of the fundamental theorem of calculus for v and u, and so it will be what that theorem says, that since this is a definite integral, it has to be u of b minus u of a, one component this one, another is I times v of b minus v of a. But if you look at this, what are these u and b? It will be equals to, I can separately write it as u of b plus I times v of b minus u of a plus I times v of a. Now giving back the values of this u and v to these points, I can write it as, this thing will be actually f of z of b, and this will be f of z of a. So what is this thing? This thing is z of b is the terminal point. The terminal point was z1 of the contour, and z of a means the initial point. It has to be f of z naught. So you have this thing, integral over contour c f derivative z dz is equal to this thing f of z1 minus f of z dot. So that's why it's called the fundamental theorem. Because you look at, this is what we do, same thing in case of fundamental theorem of calculus in real case. But this I was proving this version only for when your contour under consideration was a smooth curve. Smooth means it was not a piecewise smooth, it is smooth as a whole. Now next case, we assume that next we suppose that z of t, with this is the kind of expression of contour, is piecewise smooth. So what it means? It means that you have a contour like this. Maybe it is smooth in pieces like this one. Say for example, let me look at, you have a contour, this one, you have a piece from here to here, this piece is smooth, then you have another piece from here to here, this piece is smooth. Let this piece be something c1, this piece c2, and you have another piece from here to here, it is also smooth, and you have another piece from here to here, it is smooth, and you have another piece from here to here, it is smooth, and you have another piece from here to here, that it will be c6. So this means the piecewise, this means smooth piecewise. Now what you are going to do, you are going to apply the first case over each piece. That means our this let this be a terminal point. C1 is a contour. C1 is a contour with it is a piecewise it is a smooth contour. C2 is also a smooth, so each piece is a smooth contour, and combining these pieces makes up the whole of the C. Now look at this, suppose it has, this terminal point is z naught, and let this terminal point be something, last terminal point has to be z1. So I call this to be something, what do you call some that z, let me call this z of t1. Another point, let me call it z of t2. Let me call this z of t3. So at each, let's z3, these points, zt4 in this way. So actually what's happening, what you are going to get, if you have a piecewise smooth contour, you are going to get a partition of this interval. We have a partition of this interval AB. You will get a partition like, let it be starting with T naught, T1, so on up to Tn, where Tn will be your point B, such that your piece, the terminal point of, yeah, what you say, you say that Z of T naught will be A, and so on, Z of Tn will be P. And in between the points Z of T1 and Z of T naught will be the terminal and the initial point of the PC1. And similarly, you are, what you say, let me write Z of Tk and Z of Tk plus 1 are the initial and terminal points of Ck, where Ck is a piece. Now next thing that you have to keep in mind, that look at the terminal point of C1 is the initial point of C2, terminal point of C2 is the initial point of C3. They are joined with each other, close to each other. So terminal point of one is the initial point of the other. We have to keep this in mind. Now what we are going to do, we are going to find the integral on this whole of this contour C, and this will give us that integral on whole of this contour C uh, has to be summation of the integral over each k, because we have broken down this contour, and make we can write the as a this whole integral over C as a sum of the integrals over each piece. This is the property of the line integrals, where k will be running from, let me, 1 to yeah, okay, it will run to n. Then, but now now this one integral inside this summation is the integral that we considered in our first case. So that means I can apply the first case here. What I will get this to be f of z. Let me start from 0, this integral that will make us f of z k plus 1 minus, it has to be f of zk. So now if you expand this sum here, what you will get, first f of z, you have to start from k equal to 0, you will get f of z1. Let me, okay, again I will be messed up with the notations, but let me write it in a different way again. This is again getting not right for me here. Let me write it here in this way. It has to be f of z of tk minus f of z of tk plus 1. So the first point that you will get is f of z of t1 minus f of z of t naught, and then next sum, substituting k equals to 0, and then substituting k equals to, again I'm getting not good, f of next term you will have f of z t2 minus f of z t1, and so on. The last term will be f of z of Tn minus f of z of Tn minus 1. So then what's happening? Look at this, things are getting cancelled here. You have this cancelled out with this thing, and in this way you will get cancelled out everything. What you will be left? You will be left with only f of z of Tn minus f of z of T naught. And what it is, what is z of Tn? Tn is the Tn is b, so f of z of p will be the term in the point f of z1, and T naught is a, z of a is f of z naught, and this is what we had to prove. So let me stop here, and if you have any query, please ask me.
ये फिर से repeat